Hello everyone, welcome back to our video class here at CSEC Math Tutor. We are looking at some practice questions today for circle theorem, and we just have two objectives. One is just to review circle theorems, we've done them before, and the other is to go through 4 questions from CXE that deal with circle theorem to give you an idea of how to go about answering these questions and to make sure that you have a little bit of practice going into the exam. So let's look at the circle theorems that we have. And the first one we want to look at here is that angles in the same segment are equal. So if you look at your diagram here, you'll notice that these two angles are in the same segment, and because of that, they have the same size. So angles in the same segment are equal. Next one, if you should draw an angle on a diameter, that is, this is the diameter of the circle, and you draw the angle on the diameter, then the angle here, as long as it touches the circumference, it is equal to 90 degrees. So we summarize that and say it as angles in a semicircle. The angle in a semicircle is a right angle. Moving on. Here we have a quadrilateral, and notice that all 4 points are touching the circumference. For that matter, we call it a cyclic quadrilateral. And in a cyclic quadrilateral, opposite angles are supplementary. So this angle at E is supplementary to the angle here at C, and this angle at D will be supplementary to the angle at B. And supplementary, of course, means that they add to 180 degrees. So this angle BED plus DCB would be equal to 180 degrees. And we can use that idea to solve many of our problems in circle theorem. Also notice that if you extend this line here, this line, extend it and produce this exterior angle here, then this exterior angle will be equal to this angle that is inside, the interior opposite angle we call it. Next, if you have a radius touching a tangent, remember a tangent touches a curve or a circle at one point only. And if you have a radius touching a tangent, then it creates a right angle at the point of contact. So wherever a radius touches a tangent, right angle, important to remember as well. And these two, importantly, if you draw two tangents from the same point to a circle, then the two tangents are equal to each other. And because of that, it creates a quadrilateral, which is a kite, when you combine the two radii inside the circle. So with the two radii and the two tangents, it makes a kite. Naturally, these two angles are going to be 90 degrees. And also this angle is supplementary to this angle, meaning that they add to give you 180 degrees. Here we have a very nice theorem that talks about the angle drawn between a tangent and a chord. So this line here is a chord, and this line PQ is a tangent. So what happens now is that when we draw an angle between the tangent and the chord, let me just put some color in there. This angle between the tangent and the chord is equal to the angle that you draw on the chord. So notice the chord, this is the chord, this angle is drawn on the chord, and of course it must touch the circumference. So once it touches the circumference and it's drawn on this chord, these two angles are equal. Same thing on the other side. This angle will be equal to the one here. And these are very useful ideas to know. CXE likes, for some reason, to pop these questions on the exam. So make sure that you are familiar with this one that talks about the angle between the tangent and the chord is equal to the angle drawn in the alternate segment. That's really how we say it. But this angle will be equal to that angle. Notice that it's drawn on it. So now, having done all of that, let's jump into this and see how we can answer, or we can apply those theorems to answering actual questions from CXE. So here we have our diagram, not drawn to scale. So it means that you shouldn't use your protractor to measure the angles. It wouldn't work. The lines BD and DCE are tangents. So these two are tangents, which means that these two lines are equal to each other. What I normally do in answering a circle theorem question is that I just go ahead and fill in as much of the information that I can fill in as possible. So before answering the question, I just look at the diagram and say, what do I have? Okay, these two lines are tangents. They're drawn from the same point, which means that they're equal. And what that tells me is that this angle here is going to be equal to this angle here, because this triangle here is going to be isosceles. So these two sides are equal. It means that this angle up here is 70 degrees. And in a triangle, you know that angles add up to 180 degrees. So this is 70, that's 140, which means that this angle here is 40 degrees. And just write them in, and other stuff that you can see. All right, so let's start with the question. So OCE, OCE, OCE. Notice that OC is a radius, and this line DCE is a tangent. So the radius meets the tangent at the point of contact, which means that it creates a right angle right there. So OCE is a right angle, and the reason is that whenever the tangent touches the radius, you have a right angle at the point of contact. You probably need to write that down as a part of your answer, giving your explanation. Well, it says yes, you're giving reasons for your answer. So your reason would be that the tangent to the tangent touches the radius and creates a right angle at the point of contact. Now for BAC, where is BAC? BAC is over here. This is BAC, BAC. And notice that we have this line, and this line here is a chord. And notice that here you have an angle between your chord and your tangent. Here it is. So this angle is between your tangent and your chord, which means that any angle drawn on this chord will be equal to 70. So that tells us that this angle up here is 70 degrees. So BAC is 70 degrees, angle between tangent and the chord. And you can finish that. The angle between the tangent and the chord is equal to the angle drawn on the chord or drawn in the alternate segment. And here we have another one, BOC. BOC. So here we have an angle at the circumference, and the BOC is the angle coming from the center. And the theorem says the angle at the center is twice the angle at the circumference, as long as you're standing on the same endpoints. So this angle is going to be 2 times 70. So 2 times 70 degrees, and that gives us 140 degrees. So that's the size of our angle there. And the final one in this question, BDC. So BDC, we already found it. And our reason can be more than, we can have more than one reason. This angle here is 140. Let me just clear this up and write our 140 in there. So this angle is 140. Now notice that this shape, let me try to highlight the shape for you so you can see it better. This shape is a kite. So here's our kite. Take the two radii and take the two tangents, and we have a kite. And with a kite, these two angles are supplementary to each other. So if this is 140, then this one is going to be 180 minus 140. So BDC, angle BDC plus angle CBOC would be equal to 180 degrees. And so we can say BOC would be equal to 180 minus 140. And that would give you your 40 degrees. You could also, because we did it before, notice that this triangle, tangents drawn from the external point are equal. So we had an isosceles triangle here. So the base angles would be equal to each other. And so we could have done it that way, that this angle is equal to that angle. And having known that, we can 70 plus 70 is 140 and subtract from 180 using the sum of angles in a triangle. Either way, whichever way, our answer is 40 degrees, and you have multiple reasons to write for your answer. Let's look at another question. Here we have a nice compound shape, and we have a triangle at this side of the diameter. We have a cyclic quadrilateral, 1, 2, 3, 4. So we have a cyclic quadrilateral on this side of the diameter. So lots of things there. We have an angle here drawn between a tangent and a chord. Very useful as well. So let's look at our question. It says in the diagram below, not drawn to scale, LM is a tangent. And the angle MTS is 23. We know that this line is a diameter because it references the point O. Notice the point O in the middle. Once you see that, you know that this line is a diameter. That's important because sometimes we can see a line and assume it's a diameter when it's not. So unless you see that O on it, or unless the question says it's a diameter, then do not assume it's a diameter. All right, so let's try to answer this question. We're looking at TPQ, first one, TPQ, and TPQ is the angle here. TPQ is the angle drawn on the diameter. So because it's drawn on the diameter, we know that it is 90 degrees. It's a right angle because the angle drawn on the diameter is a right angle, or with the angle drawn in the semicircle is a right angle. So we write our 90 degrees, and we can write our reason angle in the semicircle is a right angle. All right, let's move on. Talk about the next one, MTQ. So we had TPQ, and now we're looking at MTQ. Now notice MTQ, MTL is the tangent, and MTL meets this line, OT. So OT is a radius, and the radius touches a tangent. Therefore, when a radius touches a tangent, it creates a right angle. So MTQ is also 90 degrees. And angle, the reason for that is that the radius touches tangent at the point of contact. And because it touches it at the point of contact, it creates a right angle there, perpendicular, right there. All right, next one, TQS. 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 Now notice that that angle is not even drawn in the diagram. TQS. So let's put it in. TQS. So let's draw a straight line here. TQS. Now we have our angle. Our angle TQS. So now let's mark it. That's our TQS. TQS. This line TS now becomes a chord. It is a chord. And we notice that there's an angle drawn on that chord. Here it is. This is the angle drawn on the chord. And the angle between the tangent and the chord is equal to the angle drawn on the chord. So we know for that reason that this angle is 23 degrees. That is the reason that you would write the angle between the tangent and the chord is equal to the angle drawn on it. Sometimes it's not easy to see these diagrams, and it takes a lot of practice with going through questions like this to see it. Sometimes one of the worst things is that you're looking at the question and you just can't see it. You just can't make sense of it. And it's not because you don't know what you're doing. It's just sometimes maybe you're tired, or maybe the angle that you're looking at the diagram from. So sometimes take the question, turn it around, spin the page around, stuff like that, until you see something else. If you're stuck at a question on an exam, just move on to something else and come back to it after a while, because sometimes you're just not seeing it in the moment. But when you look at it another time, you probably will see it better. So let's look at this one, SRQ. Useful tip there for exam. SRQ. So we're looking at this angle over here, SRQ. And we need to find SRQ to know what degree it is. Now, how do we find SRQ? Now, remember that this shape here is a cyclic quad. So let me write up here. Let me highlight it first. Let me put it in red so you can see that cyclic quad. Here we go. cyclic quadrilateral. Here we go. And that cyclic quadrilateral is what is going to help us to find our answer. So TQRS is cyclic. It's a cyclic quad. And because it's a cyclic quad, and we can find this answer here. QTM, walk with me. QTM is 90 degrees. And because that is 90 degrees, we can find this angle here. Now, this whole angle is 90 degrees. All of this. So this part of the angle is going to be 90 minus 23. And 90 minus 23 gives us 57. So this angle here is 57. And what we know for cyclic quadrilaterals is that opposite angles are supplementary. And because when we say opposite angles, we mean that this angle and this angle are opposite, facing each other, so to speak. So these two are supplementary. So we know now that angle SRQ, which we need, plus angle STQ, when we add them, we get 180 degrees. And we know that this one here is 57. So SRQ is equal to 180 minus 57. And that gives us the size of SRQ, which is equal to 123 degrees. All right, so we have it, 123 degrees. Moving on. Here we have another diagram. Notice something in the questions that were chosen. Here, the idea of the angle between the tangent and the chord, it's in this question. It's in this question again. It's something that CXC does often, so make sure that you know this theorem, the angle between the tangent and the chord. Now, we have BOE. We have quite three of them to work out. We need BOE. So like I said, sometimes just use what you know. So, all right, we see this triangle BOE. That is an isosceles triangle. We know that because this is a radius and that is a radius. So these two make it a right angle triangle, which means that this angle here is 20. And if this is 20, then the angle here would be 20 plus 20 is 40. So this angle here is going to be 140. Just filling in stuff and random stuff. If this is 140, then notice that this angle is at the center, and this one all the way over here is at the circumference. So this one is going to be half of that. We don't know if they're going to ask us about it. Just to fill in information based on what you see, so that it makes it easier to work out. All right, we're filling what we know. So let's answer the question now. BOE, well, we've answered it, is equal to 140 degrees. And the reason it's 140 degrees is that BOE triangle, BOE is isosceles. Okay, so this triangle here is isosceles. And because it's isosceles, we can add these two angles and subtract from 180 and end up with 140. Next one, OED. Where is OED? Here is O, here is E, and here is D. So we want to find the size of this angle, this piece right here, OED. Now it's time to use our angle between the tangent and the chord. So here is our chord, here is our tangent, this angle is 42. And what that means is that any angle drawn on this chord is going to be equal to 42, granted that it touches the circumference, which it does. So what we can write is angle DBC is equal to angle BED, which is 42 degrees. all right, based on this. Angle between the tangent and the chord is equal to the angle drawn on the chord. Now, angle we want angle OED. No, so angle BED is equal to angle BEO plus angle OED. So when we add these two, we get 42, and we already know this one. We know BEO, so BEO is 20, so 20 plus OED gives us 42, and so we can simply say that OED is equal to 42, take away 20, which gives us 22 degrees. All right. So 22 degrees for that one. Let's go to the other question, BFE. 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 All right, so we want BFE. BFE, first notice that this shape, here we go, cyclic quadrilateral. All right, so the shape, in answering the question, BFED is cyclic. It's a cyclic quad. I'm not writing out the full sentence here. BFE cyclic quad is a cyclic quad. And because it's a cyclic quad, then opposite angles are supplementary. And the BFE is supplementary to that angle over there that is 70 degrees. So we can write it that BFE plus BDE is equal to 180 degrees. And we already know BDE is 70. So we have our answer. BFE is equal to 180 minus 70, which gives us 110 degrees. Okay. Next one. And here we have a diagram. Nice again. We have tangent again, which means that we're going to have angle between the tangent and the chord. Okay, let's fill in that first. What we know about this diagram? What do we know about this diagram? We know that this is a radius and this is a tangent. So right here, we're going to have a right angle. And over here, we're also going to have a right angle. Let me not draw that. It's obscuring the 35. So let me draw it a little lower. So that is a right angle on this side, and this is a right angle on this side, which means that the angle right here on this side of the diagram, this one, is, because all of this is 90, so this side here is going to be 50 degrees. This is 35. So 90 minus 35. Here we go. And 3 from 8 leaves 5. So this side is going to be 55. Okay. So we can see from the diagram that because this is our chord, this angle up here is drawn on the chord, on this chord. This is a chord, and this angle is between the tangent and the chord. So this one up here, so it's going to be 50. I did just say up here, so that is my Jamaican coming out right there. This angle here is 55. And because this angle is 55, this is our chord. So this angle between the tangent and the chord is going to be equal to the angle all the way over here. This whole angle is going to be equal to 55 degrees. All right, we've filled in quite a bit, so let's answer the question as it is written. EBF, where is EBF? EBF, we have found it. EBF is equal to 55 degrees. And the reason it's 55 degrees is that OBE is equal to 90. So in answering part 1, OBE is equal to 90. And so we simply subtract the 35 from 90. So EBF is 90 minus 35, and that gives us our 55 degrees. Second part, we want to find BOA. BOA is now let's note that triangle BOA is isosceles. Okay, so angle BOA is isosceles. Notice that these two lines, they're both radius. This is a radius, that's a radius. They're both radii, and so we have a 40 degrees here. We have a 40 degree there, and so we can find that angle at the top right there. So 40 plus 40 is 180. So BOA is going to be equal to 180 minus 2 times 40, which gives us 100 degrees. So BOA is 100, which makes sense. And AFB. AFB, we found AFB, it is 50 degrees. Two different reasons for that. First reason is that the angle between the tangent and the chord is 50 degrees, which means that that angle up there would be 50 degrees also. And the second reason is that in our triangle here, we have this angle to be 100, and this is an angle at the center of the circle, and this is the angle at the circumference. And the theorem says that the angle at the circumference is half the angle at the center, or the angle at the center is twice that one. So because this is 100, that's going to be 50. So you can write it as part 3, B, AFB. AFB is equal to CBA. Also, AFB is equal to half BOA. And either way, you end up with 50 degrees for your answer. And for part 4 is looking for OAF. Where is OAF? OAF. Now, this is a nice tricky one. OAF. So to find OAF, we need angle BAF. We know BAF here is equal to 55 degrees. We got that answer from over here on this side, where the angle between the tangent, this tangent, and this chord was 55 degrees, which is the same as the angle drawn on the chord. So BAF is equal to 55 degrees. And from the isosceles triangle here, we know that angle OAB is equal to 40. So BAF is made up of two angles. It's made up of BAO plus OAF. And BAO is 40. So 40 plus OAF gives us 55 degrees. So we can simply say 55 degrees minus 40 degrees, and that gives us 15 degrees. And that brings us to the end of our practice questions. Remember, you can find a lot more practice questions at csecmathtutor.com in the past and practice paper pages. Make sure you make use of the multiple choice questions as you prepare for your exam. Subscribe, share with somebody who needs some more practice in this and needs some more explanations. Continue to learn and grow, and thanks for watching.